Hi, I'm Stephen Hardy, Editorial Director of Broadband Technology Report. Cable network operators are faced with the challenge of meeting today's capacity requirements while ensuring they can address tomorrow's as well. Technetix has developed a technology, the Direction Neutral Amplifier, or DNA, that it believes can help operators achieve this goal. The DNA 1800 just earned a top 5.0 rating in this year's Diamond Technology Reviews. To learn more about the DNA, I'm here with Jan Ariesen, Chief Technology Officer at Technetix. Jan, what is the DNA and what differentiates it from other amplifiers?
The DNA stands for Direction Neutral Amplifier. And what makes it special is that if you look to a cable networks originally were developed for downstream only. And roughly 30 years ago, we started to add upstream. And the way how we did it, we put filters around the active devices so that we had a downstream part and an upstream part on the same cable. That is how a cable networks evolved. And over the last 30 years, that is upgraded with different frequencies, more speed, etc., to bring to the homes. But the architecture of the amplifiers is still the same. You have filters and you have a downstream part and an upstream part. The DNA is different. The DNA doesn't use filters, and that's why it is a downstream and upstream amplifier that has not really a filtering function anymore. That means that every data that comes down gets gained down, and every data that comes up gets gained up. But it doesn't matter anymore on what frequency it is. And that will change the architecture of a cable network.
And so will the DNA support the deployment of DOCSIS 4.0?
If you look to DOCSIS 4.0, it supports a number of different technologies. Where you talk about frequency division duplex, or you talk FDD, where you can have upstream and downstream effect between each other. Or you can have full duplex DOCSIS, where you have upstream and downstream on top of each other. And when you go to extended spectrum DOCSIS, ESD, then in fact what you have is you just go to a higher frequency to create more data. If you look to the FDD and the FDX solutions, of course, we don't use filters. And that's why if the upstream and downstream are interleaved and between each other, it doesn't matter, or on top of each other, it doesn't matter, because everything that comes down gets gained down, and everything that comes up gets gained up. So it both works in both directions, because we have no filter function anymore. If you go to extended spectrum DOCSIS, is a little bit different, because now we want to upgrade our networks from 1.2 to 1.8 gigahertz. And the higher the frequency, the higher the loss in a network, based from coax, cables, passives, etc. They will have more loss on the higher frequencies. And this higher loss, of course, requires more gain to overcome it. But amplifiers are already maxed out. And if you want to increase the level to compensate the additional loss you get on the higher frequencies, you either have to go to extremely high power consumption, but still then it's almost impossible to achieve enough signal. And then if you have that signal, the quality will be so bad that you can never drive any more good quality into the homes. So therefore, what we are aiming for with the DNA is, instead of going to the higher levels, we want to go for the medium level. We can stay on the normal levels, but still to be able to come to the next amplifier, we put the DNA in the middle. This DNA will boost the signals in the downstream and in the upstream, so we can reach the next amplifier. And that way, we don't have to overdrive the power. That's why we don't have to go to the high power consumption, and we have very good quality. And this way, we can then still deliver 4K QAM into the homes. And of course, that is what we need to have if we want to meet the future requirements.
Now, we're hearing a lot these days about distributed gain architecture. How does the DNA fit into this concept?
Now, in fact, the DNA is developed for distributed gain architecture, or distributed gain architecture is developed for the DNA. Because this is exactly what we want to achieve if we want to have good quality to the home. If you look to a traditional network where you had amplifiers with very high levels that you will burn on the network, high level, burn on the network. If we want to go to the higher frequencies and to meet the requirements for 10G, 4K QAM up to 1.8 gigahertz into the home, we need to drive either very high levels that's not possible to meet that quality anymore. And that's why what we're going to do with distributed gain architecture, instead of having big amplifiers, we're going to put a number of small amplifiers. And this way we just keep the signal alive. And this way we get much higher quality for lower power consumption. If you look to the new paper from the Cable Labs, that also says that the power consumption, the reduction in the power consumption to go to DGA will be roughly 40% lower than when you go to the big amplifiers. Combine that with the win that you will have on very good quality, overall it's a win-win situation to go to distributed gain architecture. And because the DNA is a product with no filters, you can build a DNA network that can support also flexi-split, because you have no split anymore because you have no filter, so you can move around with the split for upstream and downstream. But also what you have with this part is, because you have no split, you also have no guard band anymore. And if you have no guard band, means you have more frequency to transmit over the coax, and therefore you can have more data going into the home. So yeah, the DNA is perfectly fit for distributed gain architecture.
So finally, how does the use of the DNA affect total cost of ownership?
If you look at total cost of ownership, that supports a number, or consists of a number of different variations. When you look to CapEx, you look to OpEx, and OpEx consists of power consumption, labor, etc. In fact, all the costs you need to keep this product in your network, let's say for 10 or 15 years. So all the cost involved, that contains the total cost of ownership. If you look to the OpEx, a big part of that is power consumption. And as I just said to you, is that with the DGA and the DNA in that approach, we can reduce the power consumption with 40%. And that's why, of course, that is a huge benefit for OpEx, because at the end, this is switched on 24/7. So it's a huge saving on your power bill. But also, you have no filters. So if you want to change in the future, go to a new split or whatsoever, you never have to visit the amplifiers again. So that will reduce a lot of your labor cost going forward as well. And as you have no filters, also your upgrade cost will be much lower if you change something on the remote PHY side, change something in the home side. But the network itself is a completely transparent pipe. And therefore the TCO will be heavily reduced using the DNA in this situation. So I think if you would compare the DGA approach with the DNA, and you look to the net present value of the future cash flow of that versus fiber to the home, you will see that keep on using the coax with this distributed gain architecture with the DNA. Overall, the future cash flow will be much better than rolling out fiber to the home. And that's why we believe that this technology will help the MSO to be much more competitive towards telcos, to give them the huge bandwidth, bringing into the homes with a lower cost.
Thank you, Jan. Cable operators certainly can benefit from technology that enables the flexibility to address bandwidth requirements and network enhancements today and in the future. And as we've just heard, technology that fits this description is now becoming available. For Broadband Technology Report, I'm Stephen Hardy.